2009, that was the learning that you don't have to do difficult math. First try to solve the problem. Like Carlos said in the morning, let the problem dictate the math you're doing. So when I started my position as an assistant professor at USCB, there a senior professor approached me. He's from the health sciences, and he said they have been collecting data on students, 3rd, 5th and 8th graders, their body mass index data, their height, weight, and they calculate their BMI, and they've been collecting it in 3 counties. So they create a report, a very qualitative report with few graphs and stuff, and the report is submitted to the school district, and that is it. And it has been collecting dust in several offices. So he told me, you are a quantitative person, take a look at it. So data is a precious thing, right? If you want to make it useful, you need data. So I was excited, and I started working on this ton and ton of data there is with a lot of undergraduate students. First, we split the data different ways, trying to get conclusions. So I kind of threw everything I knew at that data, and I learned a lot of statistics to try to handle it as well. And in the process, my school actually supported this project, and they sent me to workshops and other conferences in obesity to learn about the problem. And finally, I found this very happy medium where my expertise of infectious disease could be applied to childhood obesity as well. And then the problem started slowly defining itself. So the school people, so just to give you an example, so all this data they've been collecting, so everybody you talk to, the school district people or the school nurse or the school dietitian, some people will say, oh, obesity is decreasing a little bit. Some people will say, no, obesity is increasing in our area. We anyways have a high rate. The first time, apparently I was the first person after almost 9-10 years that they collected data, I plotted a time series. It's at equilibrium practically. So it's not increasing, it's not decreasing, so it's perception. So simple things can kind of generate this research. So let me start the topic. So let me define obesity in the little bit of medical terms, not too many terms, just little bit of terms I will give you. So in adults, what we do is, if you go to a doctor, they will tell you whether you're obese or normal and so on. They'll measure your height and your weight, and they put it in this equation. Okay, this equation comes from considering a person's body as a cylinder. So if you think of the volume of a cylinder, right, that's the equation that comes. Okay, there is a derivation for that. So they calculate that BMI, and for adults they will give you, if your BMI is this much, you're underweight, this much, you're normal, and it's a very straightforward calculation. It's not 100% accurate, but this is the state of the art that we use for standard to compare, and all literature refers to BMI. For children, it is a little harder, because depending on the child's age and what physical status they are going through, whether they will hit puberty, whether they're very young, their growth rate varies. So they are supposed to be bigger or supposed to be smaller, so you can't say whether they are thin or not thin or obese or whatever right away. So what they did is, they have this huge cross-sectional data. So they collected at a single point of time, they collect data for say thousands of say 10-year-olds. I have a 10-year-old example over here. So among that 1,000 10-year-old, they calculate everybody's BMI with that formula, and then they put it into a percentile. Okay, so if you are in the lower percentile, you're underweight. So how they measure it is, say these lines are all percentile lines. Okay, so a 10-year-old boy, if their BMI is say in this green area, they are normal weight. The same age, if you have a BMI of 21, you're overweight. If you're say 23, you're underweight. But if you are older, say a 14-year-old, then your BMI is different depending on whether you're which weight category. Okay, so here when I refer to obesity, overweight and these things, I will be referring to percentiles. So if you are obese, that means you are bigger than about 85 percentile of kids your age in that population. This is also an estimation. There are issues with this because this is based on a cross section which is very old, and there wasn't a lot of diversity in the process. So recently there was a paper that says depending on your ethnicity, this should be modified. But for now, this is what all literature will refer to, and I will also refer to this standard, and I'll keep referring back to this percentiles to remind you of what I'm talking about. Now, causes and consequences, I think a lot of people are aware. Well, causes, the basic bottom line cause is energy imbalance. So you're eating more than what you're spending, right? There can be many issues why it is happening and all that, but that is the bottom line. The reasons could be some related to family, your genetics, or your environment. Say in a culture, something is defined as big or something is not. Like in Indian culture, they said if men have a little bit of a big belly, that means they are well fed, they're happy people, right? But that is not the case if you go to any Scandinavian country. Okay, so it depends on the culture also. And then if you have disease or if you have, you're taking a drug for which you have a side effect, those things can affect weight as well. Consequences, I mean, this page is not enough to put that. It is a precursor to a lot of other diseases. So itself, obesity, if that is the only issue you have in your body, it is not the worst thing. But statistically, it is seen that usually people with higher BMI will have heart problems, more likely to have diabetes, more likely to have other complications, and I can list many more. So you're probably aware, and we all know it's not the best thing on earth, okay? In the, why should we focus on childhood obesity? Now the main thing is that, you know, as a child, it's easier to develop healthier habits, and it's easier to lose weight as well, and develop healthy lifestyle that you can sustain all through your adulthood. And also overweight and obese children are more likely to be overweight or obese adults later in their life. Now in America, obesity is a major problem, and to the point that the American Science Foundation, they've actually, not science, the health people have called it a disease. It's not a symptom anymore, it is a disease if you're obese. So if you look, this is only obese people, okay? So adults, more than 30% people are obese in America, okay? And in children, close to 13, 14, about 80.5% children are obese, okay? So obese is above 95th percentile, okay, children. So this percentage of kids are over 95th percentile. If you think of 1 to 100, that's a very little space to lie in. Does that make sense? Yeah. So, and then I will show you the area where I am in. That's, we are next to this county called Jasper County. There, this obesity rate in children, just that 95th percent, is over 30% continuously. Okay, so that is, it is one of those states which is known for high rate of obesity, South Carolina. A lot of other factors too. Yes, McDonald's for sure. A lot of rural areas also big time. And just to show you context of the location that I'm talking of, this is the map of America. South Carolina is this one here. Arizona is here. Arizona is better than us. Washington DC is best, but also one thing I will very quickly point out, this is self-reported data, okay? So they call in and they will ask you, what is your weight? What is your height? Most people on earth will overestimate their height and underestimate their weight. So when you will calculate the BMI, so this might also be a reflection of how honest people are in these states. So let's take it with a grain of salt, okay? Now if you look at the state itself, this is the state of South Carolina, and this is Jasper County over here. This is Jasper County. This is Beaufort County. All these little islands is Beaufort County. That's where our university is. This is our neighboring county. And so ours is a land grant county, so we support communities around us. And this is one of the community projects that I'm doing. And again, to show you a little bit of the data, I told you we were 30% of kids were obese, right? If you add to that the overweight kids, so the darker red are overweight. Overweight is above 85 percentile to 95 percentile. So they are also at high risk of getting to obese. So whenever we do interventions, we do it on both overweight and obese kids. So if you add this up, 50%, nearly 50% of kids are in the risk area. Okay, so that is why it's such a huge problem that we want to work on. Now again, one of the ways to address, so when I started working, and I have a very good group of collaborators locally as well. So basically my goal was to address the local problem, and to learn about this, I started going and meeting other scientists, and then it's slowly, I understand it's a more wider problem that I'm addressing. Okay, but the data and a lot of logistics are based on the location where I am. So whenever they try to address childhood obesity, there are a lot of programs that NIH funds, a lot of programs to address that, teach the parents, teach the kids, and they do counseling for higher risk kids and so on. But one thing they have seen, if you do an intervention in the school setting, that is most effective. And I mean, that kind of common sense, right? In a school, all these kids are captive in a way all day. So you can tell them what to do, what not to do, right? They also eat in the school one meal, okay? So you can actually teach or attack a lot of kids at once. So school setting has been seen as the most effective way of doing any intervention on children, especially on obesity. But obesity has a different problem. The thing is, see, the growth of children is not constant, like I was saying. So if I say do an intervention and then I measure their BMI today, I do the intervention, then after the intervention I measure their weight, right? And then I can easily, mathematically, I can quickly calculate how many kids gained weight, how many kids lost weight, right? But then how do you know for sure this was because of your intervention? Because say girls during puberty, girls gain weight, boys lose weight, they lean up and grow tall, right? So if I look at the boys, I will think my intervention really worked well, and for girls they didn't. So this is a major problem in assessing whether your intervention worked. Okay, so the goal, this one project that I'm working with Diana Thomas and James Hill, is that we want to create a model that given a few weight for the children, we can estimate what their growth pattern will be. So if we can do that, then we can assess if our intervention had an effect or not, right? Then we can subtract it. So that is the goal. And also, a lot of interventions are not necessarily good for the kids. You know, they can have some psychological aspect, body image issues. So those things we have to be mindful. So before we do something, if we can do a trial run in the model and we can see, oh, this has more potential of having an effect, then let's implement that. Or we see something seems very great theoretically, but if we put it in the model, we see it's not actually impacting them depending on their age group, then we shouldn't do that. So this is kind of the overarching goal for this project. And also there is a lot of difference in body mass index, image and so on, depending on their gender, socioeconomic status and age. You will see I've put a star and bolded the socioeconomic status. I want to clarify one thing. This is very unique or this is very distinct between US and India. In US, people from a lower socioeconomic background are more obese. Okay? In India, it's exactly the opposite. People who are more wealthy, they are more prone to be overweight or obese. Poor people have nothing to eat. So they don't have, this is not a problem for them. Over there, poor people eat cheaper food, and cheaper food is bad quality. They have high fat, high salt, high sugar, they're easily available, and like Carlos was talking in the morning, like a parent who's going to job all day, right? He was referring with respect to the child care. If this parent has to work 2-3 jobs, that parent doesn't have time to cook. It's easy to drive through a McDonald's, you get $1 burger. You can feed your child. Is it more important to feed my child or feed them good food? A parent will first want to feed a child, right? So you can't blame them, but this is what the reality is, that poor people over there are more prone to obesity and all the associated diseases. So I've already explained the main goal. Now this first I will show you the existing model. This is a model by Diana Thomas. Here we are treating obesity as an infection. Okay, infection as in, if you look at the susceptible people, you can become exposed, that you are likely to gain weight. This is an adult model, okay. So you are likely to gain weight, either you are born genetically that way, that you are prone to gaining weight, or you are in association, your environment gives you that nudge that you are likely to gain weight. So once you are exposed, you can become overweight by gaining weight. Then you can gain further, you can become obese or extremely obese, and these are the BMI numbers. And then again you can lose weight and come back, and from overweight you can go all the way to the recovered class. And we split the recovered and we do not put them directly to susceptible, in the sense that once you lose weight, you are actually more likely to gain it again. Okay, so it's opposite to infection. If you are recovered, that means we can almost think they are susceptible, right? There are less chance. But here, people who suddenly lose weight, they are more likely to gaining it back. So we put them in the recovered category, and then they can move back to exposed and the whole cycle as usual. So all of these result in these equations, and we can plot them. And in this paper, Dr. Thomas, she has done the plotting for United States and UK, and her result was that basically we are now at an equilibrium. So because people were trying to see whether it's increasing, decreasing, they thought it was decreasing actually. So people were very optimistic. But it is a typical infection model that goes up and then it goes down, right? But then if it's going to settle in an endemic equilibrium, what's the point? So this is where she proves that it is settled into a endemic equilibrium. So we really need robust interventions to make any change to that trajectory. There's actually 3 or 4, but 3 for each, because this is census data. So you will just not get more. But this is, the shape can be gotten with this model. Now what I have done is, for the school children, I have modified the model. It's a simple SIR model just like the previous one. Here, and also I have made the picture pretty so I can present it to high school students and they will be interested to look at it. And this was in the Siam news also with this picture. So here we will have the susceptible children, and this represents a couch potato basically. So if you're sitting and watching TV all day, not doing activity, you will gain weight. So you will move into the overweight. So overweight again is 85th to 95th percentile. Now obese class, I have actually split it into 2 pieces. The obese I am calling is from 95th to 99th percentile, and above 99th percentile is extremely obese. Now the reason we split is, this extremely obese is actually, we are talking about people who are so obese they have difficulty moving, right? They can't walk and all that. So that is a very high level, and especially for an infection model, it's important to split because they will not participate in infection. Okay, so here the concept is, first you will notice there is no exposed class. Okay, the reason is all these kids are in the same classroom, so they are all exposed anyway if we are to consider social interaction, right? So they are all equally exposed, so they are not put in a separate class. So we have susceptible itself is exposed. Okay, then this infection term has this alpha spontaneous weight gain, which is not related to association, and then we have infection from the overweight class and infection from the obese class, but no infection from the extremely obese class, because that is not a behavior you would like to emulate, because you look at the situation where they can't move or they can't sleep and all those, you wouldn't want to be like that. So
what proportion of people are the children are extremely obese?
About 8% in my population. It's shocking when I show you all the other data. So this is the modification to the childhood model. And most of you who are done some SIR model, you can look at it and you'll be like, yeah, I can solve this model, right? And we know we can solve this. The major issue here is getting the parameters, right? Now, one other thing I want to point out, here I have immigration into every single class. The reason is, my children, my data set is from 3rd grade to 8th grade, right? So when people are, it's not birth. So when they come into 3rd grade, I already know their weight status. So I can't put everybody in the susceptible class. So they go into their own classes depending on their BMI, except recovered, because I cannot know who has recovered. So anybody in normal weight goes to susceptible, and then we have the other weight classes. And I have the outgoing rate, which is usually the death rate. I have put G, it's the graduation rate. So basically how many kids are getting out of the 8th grade. So in my system is 6 years, so 1/6, usually like lifetime. That's kind of the one we have. Now this model was nice and seems like it would work, but then this is this whole parameter situation. Now to estimate these, I have been working on a lot of parallel projects in the same location. This one thing worked out for us. So in the school system also, I'm working with the school food service director, the school nurse, the school dietitian, and the superintendent and all are also involved. We want to do something in the school that will help the children. So again, I'll point out this school district, this Jasper County School District, is a very rural district with a high proportion of minority who are more affected with this obesity issue, and also they are less economically stable people. So that is why, that is one of the correlations with obesity actually. So this grant we had written to TCC Morehouse through National NIH Minority Health and Health Disparity. And here what we wanted to do was, we wanted to put a salad bar. So the general idea, if you tell somebody I want to put a salad bar in this rural school cafeteria, they will say the kids will not eat, because they are not used to that. It's expensive to put a salad bar versus putting other food, okay? Because it's high turnover, it goes bad and all that, so people don't want to invest in that. And our dietitian, she's the PI of the grant, she really believed that it would help the children. And the school authorities would say, oh no, only the skinny girls will eat this, so the thin girls will eat salad because they are conscious, nobody else will eat it. So her point was to prove that is not true. So this study is to study the association of eating salad. So association of race, gender, age and BMI and socioeconomic status to salad bar usage. So we measured all the kids in the beginning of the school year in fall, then we put the salad bar in. In beginning of spring we gave them lecture every single class, and then again at the end we measured the BMI. The goal was not to see who lost weight or gained weight, we wanted to see the association. Okay, and it's little funny that I'm a mathematician, I never collect my data before this. I am this, very privileged people, data comes to me and then we work on it, okay. So this was one situation where I was completely involved in conceptualizing the study, what the data analysis is going to be, and here a lot of our undergraduate students were involved in this also, which is part of the grant to train students. So me, a mathematician, I am in this school district and I'm measuring kids, their height, weight, right? It's a great experience, but it's every time I think, like when I was in graduate school, I didn't expect myself doing this, okay? But it's the drive to solve your problem that you want that an answer. So I will do anything that I can to get the answer to solve the problem in my community, and that's the drive. So we train our undergraduate students, so everybody who works on this project has to be IRB trained. So they need a training on handling data and handling subjects and so. So every student, I train this. Then every student who comes in contact with the school children, they have to have a thorough background check, criminal background and all that. So we do that. Then we take all our kids. So for this one, for measuring, we contacted our public health and health promotion majors. So those kids, it was good experience for them to have to go measure the kids. So we took them. Then the salad bar was put in and we recorded. So all the kids who go into the cafeteria, they swipe a card to get food. The food is free here, okay? They swipe a card and they have 5-6 stations, and I'll show you the food options. They can eat from only one station every day. So that is one question that I always get is, how do you know a child didn't take the salad and throw it away and then they got another food? Because they can't. If you swipe your card, you can swipe only once every day. So there is a probability they threw away the whole thing and they didn't eat anything, or otherwise they ate the salad. So we assume whoever swiped their card in their salad bar ate it, okay? Then we gave this lecture. So every single classroom, we prepared this lecture with the help of the dietitian about healthy lifestyle, not losing weight, because you don't want a little kid to worry about that, because they need the protein, they need the fat for their body to develop, be strong, right? So we teach them, you should exercise, you should not watch TV for more than 2 hours a day or any screen time. So those kind of healthy education. Don't drink Coke, instead go drink water. So those kind of education. And then finally we collected the data. So this data analysis I recently finished. So I thought if I just leave you with this story and go to the model, you'll be dying to know what happened as a result of this study, right? So I'll show you a few glimpses. So this one, as you probably expected, this is all so the red bars here are the number of times the kids ate the other food, okay? In the fall, in the spring is the green, and the red is the fall semester in August, what food they ate. For both semesters, a very anti-climax to the story, salad was the least eaten food choice, okay? Because what were we competing with? Think about a 10-year-old, 12-year-old, 13-year-old, right? This is a middle school. Their choices are burgers, which comes with fries, hot lunch, which is also relatively less popular, but it's a healthy choice. They have rice, chicken in a stew and those things, but that's also relatively little less popular. Then there is chicken sandwich, pizza, hot dog, chicken nuggets. I mean, who will eat a salad, you know? So it was not, this graph was very partly depressing in a way first, but there is silver lining.
So it's very interesting to see between fall and spring.
Yes.
Difference. Yeah, the difference between fall and spring. For example, taco, I would have never realized, especially in South Carolina, to be on top.
Right. Now, one thing also to point out, actually I didn't want to go too much in detail, but because you asked, taco is served only once a week. So because it comes only once a week, it's a novelty, kids want to eat it. Yes, it's special food. Also the same with pizza, it's only on Fridays. So the kids like to eat that. Salad and hot lunch, the two lower ones, they are served every single day. So whenever there is a new thing, they will go try that. Okay, so we kind of after the first fall semester, we wanted to ban pizza and ban chicken nuggets and stuff, but no, we didn't, you know, I mean, they're kids at the end of the day.
So and saying like serve salad
only few days a week. I don't know if it serves the purpose though, right, for healthy eating. And I'll show you a couple more graphs, then you will see. So another thing, see in the spring it's fewer salad, right? So there were two hypotheses. Is it because of the cafeteria servers told us it's because of the season. That year, like last year, it was after 20 years, it snowed in South Carolina. It was cold, okay? It's usually not very cold where we are in the south. It's mostly hot, 2 months of winter, which is barely like Delhi. That's we don't have snowfall. After 20 years, it was so cold, people stopped eating salad in January and February. They wanted to introduce a soup, a hot soup, so they would go. But then that messes with my statistics and my data. I cannot alter the food then if there is increase, I won't be able to distinguish what was the cause. So they actually put this, the soup for a week in December, and once I got to know, I made them take it away, and I can't use that December data anymore. And those people still hate me for that, because they're like, it's a good option, the kids will eat more salad, why are you so mean? But I am thinking, this is a study that has to be kosher. I have to analyze the data, submit a report. I can't just alter the intervention midway, right? So anyway, so that was one hypothesis that they had. It's because it was in the winter, cold months, they didn't want to eat salad, they wanted warmer food. Yeah. Right. So I will repeat your question. So she said, is the salad a full meal? Because the others might be more filling. And these are kids who just eat one time in the daytime, right? But I will like to point out, and I don't have all the slides for this study, but this is actually, they serve some carbohydrates. So there is a toast or crackers. They have chicken or some meat product. It's not only leaf salad. They have nuts, and they have legumes like chana, chola, rajma boiled to put on the salad. So if you make a full bowl, it should be filling. And they have a milk, they can get milk and juice and a whole fruit as well with the whole thing. So it should be okay. And next one, this was our biggest achievement, and like that made us feel good. So this graph is on the x-axis is BMI percentile, okay, and on the y-axis is frequency of salad bar eating. So how many times a kid goes to the salad bar. So every green dot here is one kid, okay, and it's plotted against their BMI and how many times they visited the salad bar in the whole one semester. And if you see, the bigger cluster of dots is in this area. Do you notice that? The taller points are in this area. So that is the success and the hunch of the dietitian. She said that the kids who are heavier, they want to be healthy. They want to do things that are good for them, but their environment does not always support it. Oh, I thought you had a question. So this was our big aha moment. Keep on looking at the data. Finally, you find something that is silver lining. And we are very happy to say that after these results, the school district actually kept the salad bar going. The 1 year, the grant paid for the salad bar. After that, the school district has kept the salad bar. And they also introduced a new one in the high school last fall. Okay? And that's what answered some of our previous questions. So remember, I told you we were not sure, was it the seasonality or the novelty? Were the kids eating less salad in spring because they were bored of it, or was it because it was cold? What happened, even in the high school, the first semester they were eating the same average, but once spring started, it really dropped. So we think it is the novelty, and also it's the novelty effect, because also the middle school in the fall semester it didn't pick up. You know, it didn't go back to the green bigger percentage. So at least I am spared from being scolded regularly about not putting the soup in there. So seasonality is not the issue. It's just that it's a common thing. They know they will have it every day. So the thing has reached an equilibrium because it's this audience, right? Now going back to why and how it relates to my model. So remember, in my model, we had the alphas and betas, the rates that they go from regular weight status to overweight, overweight to obese and all that. So that we didn't have a way of measuring, because all my data, you can't find the same kids' data twice. This one gave us that data. So I have exactly 1 year, and I have close to 600 kids that I have measured in the fall and measured in May. So in September to May. So I have weight change in 1 year. And year is the unit of time in my infection model. So I have direct estimation of my parameters from here. I don't have to use data fitting. Okay. So here, if you look, this in the blue bars are proportion of kids from the normal weight category who moved to the overweight or obese. So that is that rate, that alpha plus ki plus ki1 plus ki2. Then these rates from overweight to normal, what percentage moved, that is rho 1. And then some places that I had to do some assumption is, if you look at the obese, we had obese people going to normal weight also within that 1 year, okay, and also we have normal people going to obese, but those my model doesn't allow, because if somebody is going to become obese, then in the process they've gone through the overweight process, right, they've gone through that box, so I have just added it on to one of them to estimate the parameter. And then this is gives us estimating most of our parameters in the model. So here if I look at this, most of these are from our data. A couple of them I have had to use the adult parameters, and when I do that, we get a moderate fit to the data. We're not able to capture the rise yet. So we are missing some mechanism in our model. So the model needs to be modified to capture that bump, if you see, before it settles down. So there is more work to be done in this project. Now the results is that we are just moderately successful. We need to do some sensitivity analysis, plus it's a deterministic model, as you saw. So I got this one value from this one study and I show you that one trajectory, right? But we have to see what is, maybe we can put some stochasticity and see what other variations, because if I collected this data again, I'm sure the numbers would be different, right? So I have to keep that in mind and test those things as well. And then we are trying to do more impacts, and I'll skip this and move on a little bit so we have time for the workshop. And in work in progress, we still have to adjust for different racial groups, different genders. If you split that, all the parameter values will change for every single group. So there has to be some subgroups that we need to consider, and depending on socioeconomic status and all that. And the final goal is to have this comprehensive model where we will have this height and weight, and we will predict their BMI, right, for every kid. And then we will feed it into, this is the SIR model that we will feed it into, and then we will be able to make the prediction. This is the final goal. We are still working on this project. And this is my collaborators and all the funding. So this is Dr. Diana Thomas and Dr. James Hill. She is a mathematician, and among the only 2 mathematicians who do modeling for obesity in the US right now. Dr. James Hill is an obesity scientist, a very famous, he's one of those people who made this science people say that obesity is a disease, so that funds could be allocated to research on obesity and all that. And this is my local team. She is Valerie Mulemill. I kept on referring to the dietitian. So she is the one who has the hunch, and she has been collecting all this data from 2006, but I showed you only from 2009, because before that they were collecting by hand, and all those papers, somebody lost it. So I can only work from 2009 data onwards. And this is the food service director for the Jasper County School District. She's a 75-year-old feisty lady. Everybody will listen to her. If she tells something needs to be done, the school district will listen to her. She threatens to retire every year, but we are holding on to her for her life, that we can still make changes. And this is my colleague who gave me the data, and he's still very involved in the project. And Brenda Hughes, she's the grant director in the South Carolina Department of Health and Environment, and she does not like her picture put on slides. So her picture is not there. I can't finish a talk without bragging about my students a little bit. A lot of them have graduated now, but this group of kids here, they presented this poster on one part of the salad bar study. They presented this in our University of South Carolina system, has 11 campuses, and there is once a year a poster presentation from all campuses they present there. They got the first prize in the public health category, so I'm very proud of them. And this is my current student. She's working on the modeling project, as you can kind of see from that poster. This is just SIAM conference last week that she presented the poster. Yeah, so that brings me to the end of the talk part. I will take a minute to just say that I'm very grateful to the organizers for having me here. It was a great experience. And on a personal level, I went to US in 2005. I did my PhD, did my postdoc and position. So for 13 years, I've been in the field. And today is the first time that my mother is sitting at a talk. And thank you to the, and most likely, my dad is watching the live stream as well, if he is. And thank you to Anuj and Dr. Vamsi and everybody for making all the arrangements and making this happen. I also had the privilege to go to the girls' campus yesterday in Anantapur. And I'm very touched by all the philosophy of Swami. That he believes, and Jyotsnam, she told me that he believed that girls can do everything that boys can do. And that is the model that they have built the campus on, and that's the training that they have. And still in India, you know, we have this situation where girls are not always treated equal. So I take this opportunity to thank every Indian parent who thinks that their girls can be independent and be successful. And thank you all for having me here.
Talk about there were some people they were interested in knowing how you got into connected with people who are working in empirical work, because you are a mathematician. So how did this relationship build, and over what period of time, and what are the challenges that you faced during that time?
That's a
I think
very good question.
If
Yes.
you can elaborate on that thing, and also a Dahari example, for example, you can also talk about that.
Right, thank you, thank you. So my PhD was very theoretical. Like I said, I did modeling and also published, my first paper I published with Anuj also in hepatitis C. So after that, because I wanted to do work in more data related stuff, and in my field, Dr. Dahari, Harel Dahari, who's also a colleague of Dr. Dixit, who presented before. So they do work with real patient data. So immunological data of patient is very hard to get, because it's like the same person has to be pricked every day to get their viral load. So it's very rare data, and when a doctor collects that, they send to the experts only, and you can never get that unless it is published. So I knew I used to work on his paper, so I went to SIAM conference, and I knew he was coming, and one of my model is based on my thesis model. So I invited him to listen to my talk. And he liked the different approach that we were using. So later on, he took me as his postdoc. But I was doing long distance because I also had a job elsewhere where my husband was, but he is very flexible. So that is another thing. I've always had mentors who are very cognizant of the fact that family is important and women have a timeline and so on. So I've been very lucky that way. So I've continued to work with him. So that was a big exposure. Like I said, I worked with no mathematicians. There were no mathematicians in the team. So you have to learn their language and you have to learn how to communicate. So it comes down to basically, I would say, does this cell bother this cell or it doesn't bother this cell? They would say yes. I'm like, okay, then there is an arrow here. Okay, does this kill this or no? So you kind of have to figure out how to communicate. So I had some training over there, and then when I started my position there, this one of my senior faculty in the previous slide, he brought me this, and he already had some connections in the community. So I had that advantage. I didn't have to go fresh, because fresh I started and then I was not getting any feedback. Then when I went with him and I was open to doing what they want to do and how they want to do, and that is very important, because in our mind we have a certain image of how things should be, right? I go, I do this and I get the data and this. But there is a lot of bureaucracy involved in everywhere if you have to work. Everybody is answerable to another person. There is fund shortage and all that. It's just a lot of patience, I guess, and to show the people that you care. It's not because I want to publish a paper that I want to do the research, and that was always not the goal. It was because I want to address that issue, that I want to find a solution, and I think being able to communicate that is very important, and being patient. took a lot of time to get to this point also. I was talking to them, I was making their reports, but there was nothing was moving forward because it was hard to publish those also. So as a professor, I wasn't getting publications, right? I have to go up for tenure, publication list they will look at. So I was not getting publication. So I was also working on other projects that were giving the publication, but I really wanted to do something in this field. So I kept on going back to them. And one day I found this grant opportunity, and I knew what they were looking for. So I found a way to marry these two things. So they got the money and we could actually do an intervention. So things started clicking slowly, especially the grant helped.
So, as an extension, I wonder if, have you thought about parents of obese children? Are they obese?
Most likely.
Does that happen for rich and the poor? I mean, in the comparison that you made?
The correlation is very high.
Very high.
Very high correlation.
So I mean, like, so in India, the
Across-
rich parents are of obese children are obese.
In
Is
India,
that-
I haven't done the
done
data.
that study
I haven't
versus-
looked at the data in India at all, actually.
I'm just curious, now that you said that fact, I'm curious if it translates to the parents at the next level
Right.
in the US and India. So
Right, and I'm interested in working in India and looking at the contrast as well. I'm sure there is more contrast that I'm not aware of, you know. If somebody points out, yeah, I know that, I've grown up here. But from a research perspective, sometimes it doesn't click that
because
quickly.
you said most of, when kids are in the school, that's one place where you can have a control thing, right?
Yes.
Well, another place where they are is with their parents.
Yes.
So parents
Yes.
is a control.
Yes.
So if there is a way that something can be, brought in from their side, then, but if they are not following the rules, then it's a problem, right? So
That's the problem. I have a colleague in Alabama, which is also one of the dark red states that you saw. They are doing home-based interventions where the scientist goes, they have to they have to follow certain rules, like don't put cookies outside, okay? You hide them in the closet. So the little changes that they can do, or when you're sitting down to eat, don't put the rice on the table, keep the rice in the kitchen. Put the salad and vegetables on the table. So you would think twice before you have to walk back to the kitchen to go get the rice. It's easier to take a serving of vegetables. So these are the ones I remember. There are more these little behavior changes, home-based, that they can do. But one of the major issue is the socioeconomic status. Because like I said, if you're running 2 jobs, you come home at 11 at night, you're just thinking about what I can feed my kid and put them to bed. There's not time to cook. But there are interventions, which is one of the next steps that we are thinking of, is how to make quick, healthy meals, even from canned food. So you don't have to go buy fresh grocery, it can go bad. Canned stuff, you can canned peas, canned vegetables, canned meat. That is also relatively healthier than buying that burger at McDonald's. So that is one thing we are doing. We are also looking at doing a summer food truck, because kids in the summer, they gain a lot of weight when they come back, and it's hard to shed that. So in the summer, and also there are actually poor kids who don't get to eat in the summer, in the lunch time as well, because nobody's there to take care of them. So those kind of other community-based interventions we're looking at, but family-based is our top priority, just very hard to implement. But that's the golden standard. Any other questions? Then I'll move on to just introduce what I will do at the workshop. So in one of the things that I showed you, that big model where we want to finally do stuff, one of the things is we want to figure out height, right? Height and weight, so I can do the BMI and so on. This height model, actually goes very old. People have been trying to study these things for a long time. This article, this data is of a single boy whose father, it's most likely his father's mobilier. He took his height and weight every 6 months and he recorded that, okay. And this is one of the oldest complete data set that we have. And this data is referred in the literature as Mobilier's son, okay. It's from 1977. And we all use that. when I read this paper, and it's very hard actually to get a full data set of a child from almost birth to 18 years old. Apart from this, there are 2 Belgian boys and 1 Polish girl that we have data for. Okay, and then there is another group of scientists in a university in America, I'm not going to mention them, who have done this empirical study. They have a lot of data, they will not share with anybody, that's a separate story. So when I read this paper and I found this, my son was 2 years old, okay, and I thought this is my ticket to fame. All I have to do is measure him every 6 months, everybody will know this data set as Debroy's son, right? So I was hell bent I'm going to do this, and I thought it through. My son uses my husband's last name, so he won't have identity issue, nobody will know that it is his data that I'm always presenting and it's in the literature. And I decided I'm going to do that. Every 6 months I will measure him, and he will be known, and the data set will be known as Debroy's son. But then I realized I actually have to go to the doctor's clinic to measure him, because if I measure him at home, it's not viable data. And then that failed. So if anybody here wants a shortcut to fame, think about it when you have kids. That's something you can do very easily, okay? Now this paper, because it's a historical paper, I just like to show the data set. It's in France, so it's measured in peds and pounces and ligands, things that we don't use anymore. And here you will see, here you see this conversion into metric system. And then this one is another paper which has from 1989, and it has listed bunch of models. It's a review paper, so it listed different models that should be good for predicting height, okay. But back then, the statistics and stuff were not so rigorous. People didn't report as well. They don't report significance, they don't report p-value and things. So it's very hard to tell which one is better and which one is not. So we want to test these models to know for ourselves what works. But like I said, there is not enough data available, right? And this one group that has more than 200 kids that they have collected this data, we have requested and we didn't get. So at some point we got upset, and I decided, okay, you're not going to give me kids, I will create my own kids, okay. So what we do here is we create our data just using R, okay, and using some little bit of statistics. So what we do here is, this is a sample of what kind of kids you can produce. This is from 8 to 18 years old, what we are looking at, because that's the age group that my children in my community are. Plus from birth to 8 years is a different story, and the later is a different S-shaped curve usually. So here what the algorithm we are following, and you have seen first you need a plan and then you write your code, right? So the plan here is you choose a height, what height the person should be at 8 years old, and what height you want the person to be at 18 years old. And then in between, if you think about it, I'll just put some growth here and there, I can figure out a growth curve, right? But there was more to it once I started writing the code. So first you have to create a growth rate vector, because everybody has that one growth spurt where suddenly they grow in height or weight, okay. So predicting that is important. So everybody, we have to keep track of that. And then we have to give little bit of growth rate before that period and after that period. So all of this is random and it depends on, we don't know. So we all use the normal distribution and uniform distribution to create that data. And that's the exercise I want to do for the workshop. So I have the R code. Is it possible to distribute the code to everybody at now or later? Later is better? Later, okay. So what I will do is, if I can have the lights on, please. I will show you the code. Let me, how many of you actually have a laptop? Great. Do you have R installed in there? Awesome, awesome, perfect, perfect. Okay, and even if you don't have R, like you did for Dr. Padu, if you can just, if the translation to MATLAB will be very quick, and you can help me with that. So I have mine in a RStudio, it's an editor. Does anybody use RStudio? Okay. It's just an editor, so the benefit of RStudio is you can see all the screens together. So you can see your script here. This is the console. Usually when you open R, this is the part that opens where you write your commands and you run things. This is where all the intermediate stuff that I'm creating, I can see all the vectors and matrices, they show up here. And this is for all the plots. You can see the plots there. So that's the reason I like this one little better than some of the other editors. And another thing is, I won't ask you to download it now. It takes a little while. They were very very nice to me, and they went through the pain to download and install and everything for me in this computer. So what I will do is I'll just go through some of the steps. So here if you see, first the height at 18. So if you have a computer, just name this and put your own height in centimeters, okay? Just put your own height. Define height 18, the first line of the code, and put your own height in there. This line. So they can have the code at the end. I was going to go through, explain. Oh, okay. Okay. So first here I have tried to comment more or less. So here is the whatever final height that you want, that's the first line. Then the next one is number of boys you want to, this is for boys only. So a lot of the numbers that I have used are from the means and standard deviations or stuff from the NHANES data. So NHANES is an organization in US that collects cross-sectional data. So in a certain year, they will measure a bunch of kids in the same different age group, like 200 kids in each age group. But we don't know which kid is which. They don't do the same kids every year. So it's a cross. So you can get an average height, weight for every year, but you don't know exactly how it is changing. Okay, so I have used those percentages from NHANES boys data. That's why this is for boys only. And then I create a matrix where I will store it, all the boys. So let me show you the matrix here. So the matrix will look like the first column, I have the age, 8, 9, 10, 11, 12, up to 18 years old. And then here it should be 0, but I actually sourced the whole code. So let me do one step at a time. So I've created a 0 matrix, right, for 2 columns. So I'm just doing one boy. So 2 columns. The first column I will put there age, all the ages and all the numbers for all the ages. So now your matrix looks like this. And I also want to record the age at which the height growth spurt happened and all that. That is for double checking to make sure the data is making sense in biological sense. So I'm recording a couple other things over there. Now I go and I create this template for plotting. So if you look at this plot, you will see that I have type N over here. So this only creates the window, it doesn't plot anything. Okay, so once I go through the loop, it will start plotting. So this is just an empty plot that is made here. Then I create a growth velocity matrix, because to make sure that the child that I think is the child, mathematically I can put a lot of things, but that needs to make sense biologically to make sure all the heights are positive, and then you're not decreasing in height and so on, all that. So I create a separate growth velocity matrix vector, so I can always go back and double check if there is a problem. So here I take the mean height and standard deviation of 8-year-old boys. So I make a random, so here the k equals 1 and while is the iteration loop that I will start. So before that, for this height at 8, I'd have a normal distribution from that, and I'm drawing a random child. So random height I'm drawing, and then I define this, put it in my matrix. Then again I'm drawing to make sure that I get a age for when the growth spurt is happening. So it is seen that it happens within this age group between 13 and it's plus minus standard deviation. So I again have a uniform distribution where I am pulling from. All this is, a lot of this is subject to change. You can use other distributions if it makes sense and so on. And then this way I slowly define basic growth spurt. Then the remaining slots I divide by 9 and I split it up. Just one extra thing that I am doing is I am putting the smallest value in the final stage, because we always see that S shape. So I was not getting the S shape before, but we know kids grow in the S shape. So I put the smallest value as the last age, so it tapers a little bit at the end. Okay. So here if you go through the code, it is just if you don't understand something, take that piece, Google this function in R. Ultimately that is how we all code. You always Google, right? And R stack, there is lot of help on R, like Anuj said before, it's the most used statistical software right now. Lot of blogs, lot of online help. So I create this vector, and finally I'm able to create as many boys as I want, apart from the one I have given birth to. So these are like 10 kids, and it's our plots are always better visible if you export it. Not sure where it's saved. So you can have many kids who are your height, but they followed a different S-shaped curve. So thank you all for staying awake and still listening to me. It's been a very long day. And again, thank you to the organizers and Dr. Badua and everybody for your hospitality. Thank you very much.